Circular motion. In this video, we'll be talking about objects that move in circular paths and the forces that they experience. Just as a reminder, remember to pause videos on the outcomes slide to have a look at the SACE requirements that need to be met. And if you have the hard copy of the SACE outline, tick it off when you're confident with it. We're going to be investigating the motion of an object that moves in a circular path. In order to do that, we're just going to do a little bit of a refresh. So we know that speed is a scalar quantity, and compare it to velocity, which is a vector quantity that requires both the magnitude and direction. Acceleration is also a vector quantity requiring both magnitude and direction. So first, we're going to look at uniform circular motion by its definition. Let's consider an object that's traveling in a circle at a constant speed. An example in this case will be a Ferris wheel. So the velocity of the carriage has two components, its magnitude and its direction. Now, the magnitude of the speed of the carriage is not changing. However, its direction is. At one point it's going left and another point it's going right. The red carriage in this diagram might be going in the upright direction at this point. You can see in this animation that the velocity of the object is always changing in terms of direction, but the length of the arrow representing its magnitude doesn't change. So the speed isn't changing, but its direction is. Although the magnitude of the velocity isn't changing, its direction is, and this indicates that the object is actually accelerating. Now, because the carriage is not getting any faster or any slower, the magnitude isn't changing. So that what that means is the direction of the acceleration has to be perpendicular to the direction of motion. And the acceleration in uniform circular motion is directed toward the center of the circle. In this diagram here, you can see at two different points the velocity of the object is taken. Now, the change in velocity will be the final take initial, and in the vector diagram, the resultant velocity is directed towards the center of the circle. So in uniform circular motion, the acceleration doesn't change the speed of an object. The acceleration is perpendicular to the object and directed toward the center of the circle. The velocity of the object is tangential to this circle, and the force that keeps it on the circle acts as if it's always pulling it toward the center. So the force is the centripetal force, and the acceleration is known as centripetal acceleration. So now we're going to look at uniform circular motion according to Newton's laws. Newton's first law states that a body will continue to move in a straight line unless a force acts upon it. Because the carriage is not moving in a straight line, it means that there's a force acting upon it. And with Newton's second law giving the relationship between force and acceleration, it means that the carriage in this example, or the object, has acceleration. Now, in the case of the Ferris wheel, the force is provided by the arms of the Ferris wheel that connect the carriage to the central point. We can also have a look at other examples where objects move in uniform circular motion and the forces acting on them. So in the case of a car going around a track in a circular motion, the friction of the car's wheels on the track provide that centripetal force. When a bucket of water is spun on a string, the tension in the string provides the centripetal force. So both those examples can be considered contact forces. However, another example of the moon traveling around the Earth, gravity is the force that's providing the centripetal force to keep the moon in its circular motion. The following equation provides a relationship between the acceleration of an object, its velocity, and the radius of its orbit in the circular path. The direction of the acceleration is along the radius toward the center of the circle. This equation provides a relationship between the period of orbit, which is 1 lap, the radius of the orbit, and the object's velocity. Okay, if you analyze this equation a little bit further, what we have is the period here being time. We denote period with a capital T, however. The numerator in this equation is distance, and the denominator is velocity. So this equation is derived from our original projectile motion equations, however applied in a uniform circular motion scenario. So this question requires you to come up with an equation. So use the equations from this video, put them together to determine the answer. So what I'm looking for is the relationship between force, mass, velocity of the path of motion of an object when it's undergoing centripetal motion. It might help if you get your formula sheet out, look at the equations from this section and see if you can find that relationship.